This is Physics 30, Chapter 1, Lesson 4. Today we're talking about displacement vectors. Displacement vectors are shown with an arrow. They always point in the direction of movement, and the length of the arrow represents the magnitude of the displacement. So the longer the arrow, the greater the displacement. An example, if we want to add together 50 meters east to 30 meters west, we can simply draw the two vectors and then add them together. So drawing the first one, 50 meters to the east, we can represent with this arrow, and then 30 meters west would be going in the opposite direction. This gives us the resulting red arrow that indicates where we ended up from where we actually started. And this difference, of course, would be 20 meters east. So the resultant vector, the red one, is 20 meters east. If we travel 50 meters east and then 30 meters west, we end up a total of 20 meters to the east from where we began. Another example, if we add 50 meters east and 30 meters south, we can again draw the two vectors. But this time the red resultant vector is at an angle. It's not directly horizontal left or right. So in this case, we need to use Pythagoras to solve. So plugging in our two side lengths, we can get that the resultant vector, side C, will be 58.3 meters. And then the only other thing that we need is to calculate at what angle that is so that we know the direction that's traveled. Looking from where theta is, we can say that tan of theta would be opposite over adjacent, which is 30 over 50. And so we can go inverse tan of 30 over 50 to find that the angle is 31 degrees, giving us the total result that we are moving 58.3 meters measured east, 31 degrees south. Sometimes you'll need to subtract vectors. This is often the case in change of velocity, where we always have final velocity minus initial velocity. Whenever you have a subtraction of vectors, we need to convert it into an addition. So 40 meters east is fine, but then a negative 20 meters south would be the same thing as saying a positive 20 meters north. They're in opposite directions. So we can change the minus 20 meters south to plus 20 meters north, and then solve the same as the previous example using Pythagoras to find our resulting vectors of 44.7 meters, that's the red one. And then again, we need to know what angle we're moving at. So thinking tan of this angle again, we'll have tan 20 over 40. And doing inverse tan then of 20 over 40, we get that the angle is 26.6 degrees. And so we can say that the resulting vector is 44.7 meters east, 26.6 degrees north. Another example. A clock has a 15 centimeter long seconds hand, and we want to find the average speed and the velocity when the second hand is pointing at the 6, the 9, and the 12. Remember that the only difference here between speed and velocity will be direction, so if we calculate speed, we'll already know at what rate it's moving, and then we can just find direction to answer part B. So looking at average speed, we can say that the speed or the velocity will be the change in distance or the displacement over change in time. Now, knowing that the second hand is moving in a circle, when we're talking about distance here, we're talking about the very end of the second hand, the point closest to the edge of the clock that is moving around the circle. So it would be going the circumference of the circle. Circumference of a circle is 2 pi r. So we can say that 2 pi r, the change in distance will be 2 pi r over t. And we know that r, the radius, is 15 centimeters because of the information given in the question. So 2 pi times 15 over 60 seconds gives us a speed of 1.6 centimeters per second. Now the only other thing we need to know here is what is the direction. Well, thinking about when the second hand points at the 6, right at the bottom of the clock here, this is the point where the second hand was moving down and it's about to start moving up. It's right between the point where it moves down and moves up. So right at the 6, it would be moving neither up nor down. It's only moving left. So we can say at 6, the velocity is 1.6 centimeters per second to the left. With the same kind of thinking, at the 9, it's the change from where the second hand is moving left to where it starts moving right. So it would be the neutral point there. It's not moving left or right, but it's still continuing up. So we can say at 9, it's 1.6 centimeters per second up. And then at the 12, it would be 1.6 centimeters per second to the right. Sometimes you'll need to add various vectors that don't work out really nicely into right-angled triangles. You can't actually use Pythagoras. And in this case, we'll have to use something called xy component addition. So just before we get into that, we need to figure out how to determine the x and y components of a vector. So if you're given any vector, let's say something of 20 meters going at some angle, it would have some x component and some y component that would allow you to determine exactly what this red arrow represents. So assuming that the angle here is 30 degrees, if we look at the x value, x is next to the 30, so that would be the adjacent side, so we can relate it to the 20 meters by thinking about cos. Cos of 30 would be x over 20, the adjacent over the hypotenuse. Then solving for x, we can say that x is 20 times cosine 30, which works out to 17.3 meters. And this will 9 times out of 10 be true. As long as you're drawing your triangles this way, finding the x value of any vector will always be the vector length, in this case 20, multiplied by cosine of the angle. Y, on the other hand, will be the same thing but with sine. So sine of 30 would be opposite over hypotenuse, which is y over 20, and then solving for y, we get 20 sine 30. So looking for the y component will always be the length of the vector, in this case 20, multiplied by sine of the angle, which is 30. And in this example, that gives us a y component of 10 meters. So it's good practice to try figuring out the x and y components of various vectors. X will always be vector times cos angle, and y will always be vector times sine angle, as long as you're drawing your triangles in this way. For practice, we're going to look at page 29, numbers 3 to 5, 8, 10, and 11.